So just to start, a little bit about me. I'm a postdoc researcher at Swinburne University. I study pulsar timing to study pulsars themselves, things like masses and distances. I also research for gravitational waves using pulsars, and I'm also an expert in ionized interstellar medium. So I use the fact that the pulsars twinkle in the sky, and I use that as a tool to study the pulsars themselves and also structures in the interstellar plasma. For fun, I like to run and ride bikes as fast and as far as I can. So I do things like Ironman triathlons and recently started doing ultramarathons. And Matthew included this strange photo of me in his dog, looking sad in the hospital. I thought I should explain that because it was a few years ago now. I got magnets stuck in my nose while I was trying to invent a device to stop people touching their face during the pandemic. That really sort of we've heard a lot about magnetic field strengths in this talk, and I just want to point out that these were very powerful neodymium magnets that have 0.6 Tesla, so about 100 times more stronger than a normal fridge magnet. But of course, way less strong than a pulsar. Okay, so the motivation for this talk is that pulsars are awesome, and they can enable all these tests of physics, including searching for gravitational waves, testing general relativity, exploring the behavior of matter at extreme densities inside the star itself, and lots of other things, including studying interstellar plasma, the interior of neutron stars and their magnetospheres, things like the solar wind and astrophysics of stars, how they form and evolve. And so, of course, to do all these things, we need the best telescopes and the best instrumentation on those telescopes, and that gives us the best data sets possible, and we use the best tools that we can to analyze them. And so this talk, we're going to answer the question, what does the data actually look like? And we're following this chain from the telescope. The radio waves go to the receiver, which goes to a backend, which is the computer. Then we get pulse profiles. We time tag those pulse profiles with a time of arrival. We have a model that gives us time residuals, and then that gives us physics. Okay, so we're going to explore this chain a little bit more. Okay, so these are the telescopes. Pulsars are faint objects, so we want as big as the telescope as we can make. Because the bigger it is, the more radio waves we collect, and we get the pulsar data. So historically, these big telescopes have been large aperture single-dish telescopes like Parkes and Meridian. Recently, there's this 500-meter telescope in China, and of course, now we're moving on to interferometers as well to do pulsar science, such as the ECAT here, which is 64 dishes. Each one is 13.9 meters across. So these sites are chosen to be radio quiet, low levels of interference. Matthew was talking about the pristine wilderness, as he called it, of the UHF band for the ECAT. Yeah, so we build these telescopes very far away from the cities. And we get to choose what observing frequencies we want to look at with these telescopes. Okay, so we do that by designing a receiver system. So the receiver, also known as the front end, is the bit that turns the radio waves into an electrical signal, a time series of voltages coming out from the beat. So for the ECAT dishes, we have this main reflector, which then lands on the secondary reflector, and then goes into the receivers that are here. And so these are basically cleverly designed pieces of metal that the radio waves induce electrical signals in that. So when we're choosing observing frequencies, we have to take into account the fact that pulsars are brighter at lower frequencies, so you might want to go to as lower frequency as you can. But the sky background is also brighter at lower frequencies. There's also this ionized interstellar medium, and that has a strong frequency-dependent effect, which impacts the precision pulsar timing that you can do. And so the sweet spot for precision pulsar timing is about 600 megahertz to 3 gigahertz or thereabouts. So these receiver systems have a system temperature, and this basically adds noise into the data, so just random fluctuations. And so we want to lower this number. So we do this by building colder, better receivers. And Matthew went through this equation. So this is describing the amount of system flux density noise that's in our data. It depends on the temperature of the receiver, but also how long you observe, the number of polarizations, and the bandwidth. So if you observe over a wider frequency range, you reduce the noise. Okay, so at Meerkat, we have these 3 receivers at the moment. The UHF and LDAN and SDAN that Nathan was talking about. This is a figure of a receiver that's being installed on the Parkes radio telescope. It's actually already installed now. This is the ultra-wideband receiver. So you can see it's just a cleverly designed piece of metal. And so this one is activated by radio waves from over a very, very wide bandwidth, covering basically all of this band. Okay, so once the radio waves induce voltages in the receiver, this is then transferred to a backend, which is a computer. It digitizes the signal, and we end up with a time series. So very fast sampling of data. And if we are observing a pulsar, this time series looks like just random noise, there's just nothing going on. And every now and then we get this pulse from a pulsar. So this is a very, very bright pulsar where you can see individual pulses in this time series. In Australia, we like the pulsar so much that we actually put it on our first version of the $50 note. You can see it on the side here, pulses, and here's the Parkes radio telescope as well. So the backends also channelize this data into many frequency channels. So across the bandwidth of the receiver, you might have something like 1,000 frequency channels, so that can be chosen and optimized based on the science that you want to do. And so these backends can output various data types. There's just the raw voltages, which is basically a strategy of just save everything, you can process it later however you like. There's the search mode data, which Tian was talking about to search for new pulsars. And then, of course, we have the fold mode data, where if you're observing a known pulsar, you know its pulse period. You can actually save a lot of computation, or a lot of data size by averaging pulses together over a window of something like 8 seconds to 30 seconds. And the pulse gets brighter relative to noise, but also you save a lot of space. So we'll be focusing on this fold mode data. Okay, so this is roughly a diagram of the chain of events. So we have the pulsar emitting a beam of radiation, and this train of pulses is traveling through the interstellar medium. As it does that, it gets frequency dispersed. So the interstellar medium is actually slowing down the radio waves, and it does so more strongly for low frequencies. And so the pulses get dispersed in frequency. So when they arrive at the telescope, they're received to the receiver, and they get processed by this back-end instrument. We can correct for this dispersion within the frequency channels that we're forming. We also form the polarization parameters that we're interested in. And then these dispersed pulses go through a phase of pulse folding, which is where we take the model of the pulsar and then we fold this data at the pulse period. Then what we do is we take a template of the pulse profile and we compare that with our observed pulse profile. That gives us the time of arrival. We then compare that time of arrival with the prediction from a model, and if we like, we can update that model and get new parameters and new physics and stuff. So now we're going to focus on this part of the chain, from the pulse folding onwards. So yeah, as I said, pulsars are faint. So for most pulsars that we already know, we have a model of them, and so we can take the data time series and break it up in the pulse period and stack them together. From most pulsars, they're not as bright as the one I showed earlier. You can't see the individual pulses, and so your time series might actually look something like this, which is just, it just looks like noise, but there could be a real pulse in here every second or so. This is a normal slow pulsar, and so we follow the data up. The noise either adds constructively or destructively, it's just completely at random, and so the more noise you add together, the more it averages down, eventually to 0, if you add enough data together. But the pulse is always at the same place in this one pulse phase window, and so that adds the longer you observe, and so the pulse emerges from the noise. So this is an example of a pulse profile. This is being viewed in a program called PS Archive, which we'll look at later. The linear and circular polarization can be formed from the data from the receiver, as given in the colored lines here. The white line here is the total intensity, which is the brightness of the pulsar. And on the top, this is the position angle of the polarization. So across pulse phase, we can often have thousands of samples, and so that corresponds to a microsecond level resolution in the shape of the pulse profile, and that allows us to get very, very precise times of arrival of these profiles. So if we're observing this fold mode for a normal pulsar that we know the sleep period of, we actually have many of these pulse profiles in a so-called data queue. So we have one profile per pixel in time, per pixel in frequency, and per polarization. And so you can actually look at the profile as a function of any of these things, and there's a wealth of physics to learn from doing that. You can, of course, also just average over all of these dimensions and get one very high signal-to-noise ratio pulse profile, which is the average of your observation and average over all of frequency. So when we look at a pulse profile as a function of frequency, we can see lots of physics. The main stuff is all the effects of the interstellar medium. So the first one, as I mentioned, is dispersion. So if we look at frequency on the y-axis here, and then pulse phase on the x-axis, we can see that if the pulse is dispersed, the higher frequencies arrive earlier, and then the later frequencies delayed by the interstellar medium. And the strength of this delay as a function of frequency depends on the number of electrons along the line of sight between us and the pulsar. So pulsars that are further away have more electrons in the interstellar medium, and they delay the pulses more than pulsars that are nearby. We can see a few other things here. So scintillation is when the radio waves are scattered by diffraction in the interstellar medium, and this forms an interference pattern in the telescope, and this interference pattern makes the pulsars twinkle in time, but also it varies as a function of frequency. So the scintillation here is appearing as these isolated little bright patches. Pulsars, as I said, also have a steep spectrum. That means they're brighter at lower frequencies. And you can see here that this pulsar is pretty faint up here at the high frequencies, and it gets brighter as we go down to low frequencies. And some pulsars, you might also see that the pulse width changes the frequency. Typically, the pulses are narrower at high frequencies and wider at low frequencies. And this is because of where the emission is coming from in the whole of the magnetosphere. So the high frequencies can be coming from lower down, closer to the pulsar. And of course, also as a function of frequency, we can see radio frequency interference, but that's been removed as well. Okay, so in the interstellar medium, this is a diagram of what's going on. So the pulsar is emitting spatially coherent radio emission. It encounters the ionized interstellar plasma, which then disperses the radio waves and also scatters it. So the wavefronts become more distorted, and this produces an interference pattern in the telescope. So when we actually observe the intensity of the pulsar, we're observing the pulsar through this interference pattern. We're observing this interference pattern. This is moving across our line of sight to the pulsar because the pulsar, the ISM, and the Earth are all moving with respect to each other. And this makes the intensity of the pulsar vary as a function of time. And this effect also depends strongly on how far away the pulsar is. Because it's changing the number of electrons, which of course is changing this time as interstellar medium light. So, this is another pulsar showing as a function of frequency. We've corrected for that dispersion sweep. And so you can see there's more scintillation here. There's these bright patches. We also see these missing bands of data. So this is where radio frequency interference is taken out so that we can actually see the pulse. So another effect of the interstellar medium is scattering, as mentioned. And so multipath propagation means that pulses that are scattered actually travel further, and so they're delayed. And this is a very frequency-dependent effect. So at high frequencies, we don't have much of the scattering. Then at low frequencies, a very sharp pulse will get scattered and actually arrive as this almost exponential-like curve. Okay, so if we look at the pulse profiles over time, we can find some more physics. So as I mentioned, we might see scintillation because this interference pattern is moving across our telescope, and so that can change the intensity with time. We don't really see it in this plot, so we have time on the y-axis here, and pulse phase on the x-axis. So scintillation would make this eventually get less bright and then bright again. Some pulsars have mode changing, so the actual emission properties are changing at the pulsar itself, and some pulsars in fact just turn off briefly. So this is an example of a pulsar. Again, time on the y-axis here. We can see the pulsar is on, and then there's this little gap here, and the pulsar is turned off, and then it's turned off again. We don't know much about why this happens. Any guesses? Guesses? Matthew?
Why do they turn on and off?
Yeah.
We think there's like a condition in the magnetosphere that's conducive to radio emission, and maybe there's like a short circuit or something, and it takes a while for the charge to build up again to get to this state where you can generate free electrons. So the pulsars that tend to null are close, the voltage, the power, the energy for pair production is closer to the minimum required. But unfortunately, it's not a beautiful thing where everything in one part of the magnetic field period diagram does this and others don't. It's sort of more a trend.
I mean, in 1937, like, there were certain areas of the orbit where we could see beam, where it was emitting, and other places where it was not.
Yeah, so that system is very unusual in that the A pulsar is so energetic it actually distorts the magnetosphere of the B pulsar and causes the radio emission not to be like a normal pulsar. Depending on the geometry of the system, the magnetic field can be sort of squirted away from us or not as badly affected. So that's not a typical system, and you can tell whether a pulsar is in a binary to a ridiculous precision. So I don't think it's because these are in a binary, but there may be, it's also quite an old pulsar, the big pulsar. So it wouldn't surprise me if it's a little bit nulling as well.
There are also some ideas like something can disturb the magnetosphere, asteroids as a pulsar, exciting things like this. But it's a mystery. The pulsars also do weaken with time, and eventually there's a death line where they stop pulsing altogether. But this may or may not be related to those points. also just change randomly in intensity and shape. And so this jitter noise, as we call it, just varies in your pulses. If you average enough of them together, then this effect goes away. And so that's another advantage of this whole mode observing and averaging together lots of pulses and so as a function of time, we might also see sudden bursts of RFI interference. Yeah, so every time we're talking about this, this is a plot of the radio frequency interference at meerkat. As we explained these plots here, so this is the UHF band on the left and L band on the right, and this is showing a fraction of time that given frequency is affecting our data. So there's some of these mobile bands that are just always present, and we always remove them from our data. So yeah, this interference can be caused by satellites, cell phones, Wi-Fi planes, even lighting, microwaves. Okay, so this is what it actually looks like in the data. The interference can actually be quite often so strong that you don't see this pulse at all. So we do have to remove the RFI before we can do proper science, but here we've got some RFI as well as the pulsar here. So the most common form of the interference is strong narrow band, so sort of isolated in frequency, and also these bursts in time. So on the left we're showing frequency on the y-axis, on the right we have time on the y-axis. And here so most of the time this RFI is off, but we have these sudden bright bursts. Okay, so we talked about the pulse profiles and showed them as a function of frequency and time. This is now showing pulse profiles as a function of pulsar. So these are profiles of different pulsars. And you can see that they're all very different. And so the pulse profile is really just like the fingerprint of the pulsar. It's unique for everyone. The shapes and forms of these pulse profiles depends on the spin properties of the pulsars, depends on how we're viewing the beam of the pulsar, and of course the shape of the emission region. And so we can study these things, but not much is known about the emission region, and it's often quite hard to turn these profiles into a model of the emission. So in precision pulsar timing, such as searching for gravitational waves, which we'll do later on in this workshop, we're interested in these narrow pulses because they give us higher precision time of arrival measurements. Okay, so when we have a pulse profile, so we've observed a known pulsar, and we get one of those pulse profiles from the previous slide, what we do next is time tagging. So for every pulsar, we can form a model pulse profile by averaging together lots and lots of data and getting rid of the noise in that data, and that becomes our template. This is like our fingerprint of the pulse profile and our model. So what we do is when we carry out an observation, we take this template and we slide it across the data until we find the pulse phase where it matches our observation as close as possible. And pulsar timing is so precise that we can actually account for every single rotation of the neutron star over the length of time that we've been observing. So for some millisecond pulsars, they spin hundreds of times per second, and we've been observing them for 30 years or maybe more, and we can count for every single pulse of the pulsar within that time. So that's hundreds of billions of pulses for some millisecond pulsar. So we made various assumptions for this pulsar timing to work, and it does work. So these assumptions are that the radio emission is anchored to some stationary point on the neutron star, which is assumed to be the pole of the magnetic field. And the radio emission is relatively stable enough for us to model it and time it. An exception is that in relativistic binaries, the beam of the pulsar, or the viewing angle of the pulsar can process the relativistic effects. And so that's actually why the B pulsar and the double pulsar is not visible anymore. And so The assumption in pulsar timing is that the signals that we're interested in, they don't really change the shape of the pulse profile. It's stable with time. But they do cause delays. They make the pulses arrive earlier or later. And so when we find the arrival time of a pulse profile, we look at the residual difference between our model prediction and when it actually arrived, and the physics of the signals of interest are going to make that pulse arrive a little bit earlier or a little bit later. So yeah, this is a diagram of an observing session where we have multiple individual pulses coming in. We fold them to decrease the noise and increase the signal of the pulse. And then we compare it to our model predictions. This is a train of pulses that's predicted by some models, which we'll talk about next. And then at another observing session, maybe a week or a month later, we observe the pulsar again and do the same thing. We fold it, we measure a time of arrival, and any difference between our model prediction and the observation, that's where the exciting physics is going. Okay, so this is a visual demonstration of how we're doing this. So I have a notebook, which I'll show you later, that's included in the virtual machine that you all have. You can look at a simulated pulse profile, and the blue data here is just a simulated observation of a pulsar. And then we have a model, which is this orange curve. This is the model pulse profile. You can change the amplitude of this model, or you can change the location of this in phase. And what we're trying to do is minimize the sum of the square of the residuals. So the residual is the difference between the blue data and the orange model. That's this bottom plot here. You can see there's lots of structure here in the residuals. It doesn't look like just pure noise. That means that the model fit is bad. So if we change the amplitude and we change the phase by moving those sliders, there we go. The noise here looks much better, and this statistic that we're trying to minimize goes down. So yeah, we can play with this later, but yeah, this is basically how we're fitting the pulse profile to the data. Okay, this is what it actually looks like in pulsar timing in the PSI software. So on the top we have residuals, in the middle we have the template pulse profile, and on the bottom we have the data. So when we do this time tagging, we line this template up with the data, we get an error for this pulse time of arrival of about 30 nanoseconds. So that's very exciting. Okay, so the TOA uncertainties, and Matthew went through this as well, depends on the system temperature, depends on the observing time and the bandwidth, and also the duty cycle, or the width of the pulse and its pulse period. So yeah, the TOA uncertainties can be minimized by getting a bigger telescope, more sensitive receiver, or a wider bandwidth, and observing a fast-spinning pulsar with a very narrow pulse. So the best pulsars, the millisecond pulsars, can actually be time tagged to about 10 nanoseconds in uncertainty. However, the measurements often show much more noise than that. So if you look at this plot here, the error bars here seem a little bit too small for the amount of scatter that's in these measurements. And a big cause of this is jitter, so the pulse profiles changing randomly from pulse to pulse. So if this is due to jitter, we can only really reduce that by observing the pulsar for longer and averaging more pulses together. So once we've measured a pulse profile and we've time tagged it, we've got our time of arrival, we save it to a text file, and this is going to be passed on to another piece of software to actually do the pulsar timing. So this text file has the following format. We'll be using these later on in the workshop. So it has a final name, the frequency of the observation, the TOAs is the actual arrival time in NJEs, is a date. The uncertainty for the time of arrival in units of microsecond, the telescope that was used, that here is NICA, and then a bunch of flags which describe properties of the observation. So, for example, this is the template that was used. This is the number of frequency channels in this observation as well. Okay, so very good. Yeah, so anyway, timing. We have a timing model of a pulsar. It describes things like the position and motion of the pulsar. It's what's predicting these pulsar arrival times. So this is what the timing model, the model of the pulsar actually looks like. It's a text file full of interesting numbers. So these are the parameters that describe the pulsar. And yeah, it describes everything from the pulsar spin period, and how that spin is changing with time, the astrometry, so the position and motion of the pulsar. There's dispersion we can talk about. If the pulsar is in an orbit with another companion, it describes the Keplerian orbit and any post-Keplerian effects like geometric changes in the orbit or relativistic changes in the orbit. It also describes the solar wind, it's a model of the solar system, and any instrumental effects. So we've got some arrows that roughly point where each of these things are described. So yeah, for this pulsar, we've got position, spin, dispersion measure, some astrometric things, and binary parameters here. So we can go through these in more detail later on. So this file of model parameters plus the file of those measured times of arrival is given to some software called Tempo2, which is then used to plot the timing residuals. So we take all those time of arrival and we subtract the model prediction, and we see things like this. So we have timing residual on the y-axis. So again, it's the difference between the observation and the model, and time on the x-axis here. So in both of these cases, this is many years of observations. And we often see that the timing residuals are not flat. That means there's errors in the model. There's something that's happening to the pulsar that's not predicted by the model. In this case, it's spin noise, or probably spin noise. It's irregularities in the spin of the pulsar itself. On the right here, we have some spin noise, but we also have very strong frequency-dependent effects. So the blue here are the timing residuals from observations at a high radio frequency. The red is observations at a lower radio frequency, and the green is the frequency in between. So you can see that there's lots of random-looking wiggles here in these residuals, and it's much, much stronger at the lower frequencies. This is actually very small and random variations in the number of electrons along the line of sight. So this is the dispersion measure changing with time. So that dispersion sweep is changing by about 1 part in 100,000, and we can measure that very easily also. Okay, so in summary, we've gone through the journey of pulsar timing data from the telescope, which is placed in the radio quiet region, given to the receiver to transform into voltages. The back end then processes that into pulse profiles that say as a function of frequency, time, and polarization. We remove any radio frequency interference. We can sum this pulse profile data over frequency and time and polarization to get the highest signal-to-noise pulse profile that we can. We then compare that with a model of the pulse profile to time tag it with a TOA with very high precision. We compare the time of arrival with our prediction from a model of the pulsar. We look at the timing residuals and we learn a whole bunch of new things that weren't in our model. And we can update them and learn lots of new physics, including searching for gravitational waves. So I end by saying pulsars are awesome, and we'll hear more about gravitational waves in Ryan's next talk. Thank you.
So when you want to create like the pulsar profile, how many folds do you need? I know it depends on what time you have and how much noise there is, but on an average, how many
Yeah, it depends what you're trying to do. So to actually form the profile, the model of the profile, that's what we need. We just average together as many observations as we can. Typically, you would use maybe at least 100 very bright oscillations with Pulsar. So the idea is that you just want to reduce the noise as much as possible. So when you do that, you often see that there's small features in Pulsar profile, and you want to bring those out. And so, yeah, typically 100 bright oscillations, and those bright oscillations each might be 30 minutes long, or something like that. With Meerkat, it's much brighter, so you can observe for less.
And then, as it changes into, I would say, rotating, rotating, and instead rotating, how often do you need to update the profile due to those effects?
So those effects don't really change the pulse profile as much. So they'll shift the pulse in phase, but they're not going to change the shape. It's really just the relativistic precession that is going to change the viewing angle of the beam, and that changes the pulse shape. And so, yeah, our assumption is that the profiles are stable with time. But that's actually not always true. So something can happen in the magnetosphere of the pulsar, and it can actually change the pulse shape. We can either model that in the residuals that it produces, or we can update the pulse profile, but it's rare that they are pretty stable with time.
I think so. So the wiring system is forming when one is born and then the other one is getting bigger. But then the size of that one will it change how the beam like increase the other you see it. Because then like you want to get the pulse profile, but when did you get the pulse profile for that wiring system? So how big was it and at what stage did you get it? So each one has a fingerprint, but each one's fingerprint will change depending on how far the wiring system falls.
Yeah. Yeah, so most of these pulsars that we're observing, particularly the millisecond pulsars, their companions are dead stars, neutron stars or white dwarfs, and so they're no longer evolving. So they're very, very compact, and the systems are actually just very well described by Keplerian orbit, and they're very stable over billion years or something like that. There are some pulsars that are orbiting main sequence stars, so they have bigger, fluffy companions that can actually be in the process of accreting, for example, or this big fluffy star can have tidal interactions, which changes the pulses. But again, those effects are mainly just shifting the pulse in time, causing a delay. They're not really changing the viewing angle. So again, we don't need to update the profiles.
Yeah. How many processing pulsars do you have when you've seen the beam change consistent with the general
So I think there's been at least a couple that we've measured the precession rate, but only the double pulsar has actually processed out of the one of the pulses. Maybe Matthew knows the number of relativistic pulsars where we've measured the precession rate.
Yeah, so the number we've observed a very regular change is quite high. It's like half a dozen. The number where we can apply a model to infer how many degrees it's changing is like 1. So the emission cone seems to be so unpredictable as a function of the angle you're intersecting it, that all of the model predictions tend to fail. 1913, the original binary pulsar changed. 1534 changed. There's the one that had a bright pulse and an interpulse, and they've actually changed so that the interpulse is now the bright pulse, and the other one is now lower. 1141 changes. There's quite a few. Anything with an orbital period less than about a day seems to be doing. But the strange thing is the double pulsar, bright pulsar hasn't changed in a measurable way for 15 years.
20. That's orientation geometry. will rotate, so it shouldn't change because if you bring out from school perspective around, it's not going to change.
So the double pulsar is like the orbital orientation is about 89 degrees or something.
Yeah,
So if its spin axis is aligned, then it wouldn't change. But if the spin axis wasn't, it would change rapidly.
yeah, but then it must be aligned, no? What is this one?
Well, it's weird that one of them is aligned and the other one isn't, which is kind of hard to understand from an evolutionary point of view.
Do you guys know if you believe this is aligned?
So it may be that the explosion that created the B pulsar reoriented the spin axis a bit, but it didn't actually change the plane of the orbit.
Yeah, I've always wondered why you could have a spin axis, and then I assumed it was the spin axis was orthogonal to the orbit, that's why it wasn't recessing. And then why moves the beam at 90 degrees to it? Because I was like, the most naive model is that the beam would come out.
Yeah, so the beam comes out the magnetic axis on the spin.
Yeah, so why is that huge, this correlation between the magnetic axis and the spin axis and those things?
Why is there a huge one?
Why is there such a big difference between the
Spin of the magnetic axis. That lays in the realm of theory, which I don't pretend to know much.
Okay. But so you don't know.
But it might just be a very, like as the magnetospheres shrink, the magnetic complexity seems to go up. So Daniel had some nice plots showing different pulse shapes. If you actually look at slow, boring pulsars, they typically have just a small emission spike, a bit like a Gaussian. But the millisecond pulsars is much more complicated. So probably in the double pulsar, the slow pulsar has a boring pulse, and the other one we're looking in at the magnetosphere and we're seeing more of the multipolar effects. It's a little bit airway. Which is why I use pulsars as tools, not things to do theory.
Well, one thing as well, if the magnetic axis and the spin axis are aligned, then you wouldn't be able to observe it as a pulsar, right? Because it would be always being towards you. So you wouldn't be able to see it turn on and off, it just like a normal radio source. So they might exist, but we wouldn't be able to observe them the same way we observe normal pulsars.
Yeah, it could be an observational bias thing.
Yeah.
See what's on the road.
I hope you're all seeing that there's lots we don't know. So let us stay.
Okay, as there's no more questions, thanks a lot for speaking.